The National Electrical Code, specifically Article 406.6a, states that receptacles installed in a faceplate or plaster ring shall be mounted with the ground terminal toward the top. Furthermore, Article 406.6b indicates that receptacles installed on a strap shall be mounted with the ground terminal toward the top or bottom. Similarly, the Canadian Electrical Code, under Rule 26.700 footwall, stipulates that receptacles installed in a box shall be installed with the ground terminal of the receptacle at the top or bottom. The reasoning behind this requirement stems from safety considerations. The NEC and CEC mandate this orientation to ensure that the grounded terminal, also referred to as the third prong or neutral, is the first to make contact when a plug is inserted and the last to break contact when it is removed. This design feature is crucial for preventing electrical shocks and minimizing the risk of arcing. However, certain exceptions to this rule exist. Firstly, receptacles installed in wet or damp locations may be mounted with the ground terminal facing either up or down. Secondly, receptacles installed in accessible areas, such as countertops, may be mounted with the ground terminal facing up to prevent accidental contact. When installing 20 amp 125 volt receptacles, one must adhere to the prescribed ground opening orientations to ensure compliance with electrical codes and, more importantly, to maintain electrical safety. Understanding these regulations and their underlying rationale is essential for anyone involved in electrical work. The primary purpose of grounding is to provide a low impedance path for fault current to return to the source. This path facilitates the rapid operation of overcurrent protective devices such as circuit breakers or fuses, thereby minimizing the duration of any potential shock hazard. A properly grounded electrical system ensures that metallic parts of electrical equipment, which may become energized due to insulation failure, are maintained at or near ground potential. This reduces the risk of electric shock if a person comes into contact with such parts. Grounding also helps to reduce electrical noise and interference in sensitive electronic equipment. The size of the grounding conductor is determined by the size of the overcurrent protective device protecting the circuit. Table 250.122 in the NEC provides guidance on the minimum size of equipment grounding conductors for various circuit ratings. For example, a 20 amp circuit typically requires a 12 American wire gauge copper grounding conductor. Grounding electrodes, such as ground rods or ground plates, are used to connect the electrical system to the earth. The grounding electrode system should have a resistance to ground of 25 ohms or less. If the resistance exceeds 25 ohms, an additional grounding electrode is required. The NEC provides detailed requirements for the installation of grounding electrodes in Article 250. The grounding conductor must be securely connected to the grounding electrode using approved methods, such as exothermic welding or listed connectors. Proper grounding is critical for the safety and reliability of electrical systems, and it is essential to follow all applicable codes and standards when installing or maintaining grounding systems. The equipment grounding conductor, often green or bare, connects non-current carrying metallic parts of electrical equipment to the system grounded conductor or grounding electrode conductor, or both, at the service equipment or separately derived system. The purpose of this connection is to provide a low impedance path for fault current to flow back to the source, allowing the overcurrent protective device to quickly trip and clear the fault. The size of the equipment grounding conductor is determined by the rating of the overcurrent protective device protecting the circuit, as specified in NEC Table 250.122. For example, a 20 amp overcurrent protective device requires a minimum 12 American wire gauge copper equipment grounding conductor. The equipment grounding conductor must be installed in the same raceway or cable as the circuit conductors. This ensures that the impedance of the grounding path is minimized. The equipment grounding conductor must be connected to all metallic enclosures such as junction boxes, equipment cabinets, and motor frames. This ensures that all exposed metallic parts are effectively grounded. In some cases, the metal raceway itself can serve as the equipment grounding conductor, provided that it meets certain requirements outlined in the NEC. The grounding electrode conductor connects the system grounded conductor to the grounding electrode. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. For example, if the service entrance conductors are 2/0 American wire gauge copper, the grounding electrode conductor must be at least 4 American wire gauge copper. The grounding electrode conductor must be connected to the grounding electrode using approved methods such as exothermic welding or listed connectors. The grounding electrode conductor must be protected from physical damage. This can be accomplished by installing it in conduit or by locating it in an area where it is not likely to be damaged. The grounding electrode conductor must be continuous and without splices or joints unless specifically permitted by the NEC. The grounding electrode system must be installed in accordance with NEC Article 250 Part C. Grounding electrodes can include metal underground water pipes, metal frames of buildings, concrete encased electrodes, ground rings, and ground rods or pipes. Each type of grounding electrode has specific installation requirements that must be followed. For example, ground rods must be at least 8 feet long and must be driven into the ground at least 8 feet apart. Concrete encased electrodes must be encased in at least 2 inches of concrete and must be located within the bottom 20 feet of the concrete. The resistance of the grounding electrode system to earth should not exceed 25 ohms. If the resistance exceeds 25 ohms, an additional grounding electrode is required. The bonding of metallic parts is another important aspect of grounding. Bonding is the permanent joining of metallic parts to form an electrically conductive path that ensures electrical continuity and the capacity to safely conduct any fault current likely to be imposed. Bonding reduces the voltage potential between different metallic parts, minimizing the risk of electric shock. The NEC requires bonding of various metallic parts, including metal water pipes, gas pipes, and metal building frames. Bonding jumpers are used to connect these metallic parts together. The size of the bonding jumpers is determined by the size of the circuit conductors, as specified in NEC Table 250.102 cone. Bonding jumpers must be installed in accordance with NEC Section 250.92. The grounding system should be inspected and tested periodically to ensure that it is functioning properly. Ground resistance testing can be used to measure the resistance of the grounding electrode system to earth. Continuity testing can be used to verify that all metallic parts are properly bonded together. Visual inspections can be used to identify any signs of damage or corrosion to the grounding system. Any deficiencies identified during inspections or testing should be corrected promptly. Ground fault circuit interrupters, or GFCIs, are another important safety device used in electrical systems. GFCIs are designed to protect people from electric shock by detecting small ground faults and quickly interrupting the circuit. A ground fault occurs when current flows through an unintended path to ground, such as through a person's body. GFCIs are required in many locations, including bathrooms, kitchens, and outdoor areas. GFCIs work by monitoring the current flowing in the hot and neutral conductors of a circuit. If there is a difference of 5 mA or more between the current in the hot and neutral conductors, the GFCI will trip and interrupt the circuit. GFCIs are very effective at preventing electric shock, but they do not protect against overloads or short circuits. Arc fault circuit interrupters, or FCIs, are another type of circuit breaker designed to protect against fires caused by arcing faults. An arcing fault is an unintentional arc created by damaged, worn, or degraded wiring. Arcing faults can generate high temperatures that can ignite nearby combustible materials. FCIs are required in many locations, including bedrooms and living rooms. FCIs work by detecting the unique characteristics of arcing faults, such as erratic current flow and high-frequency noise. When an arcing fault is detected, the FCI will trip and interrupt the circuit. FCIs provide an additional layer of protection against electrical fires. Surge protective devices, or SPDs, are used to protect electrical equipment from voltage surges. Voltage surges are temporary increases in voltage that can damage or destroy electronic equipment. Voltage surges can be caused by lightning strikes, power outages, or the switching of electrical loads. SPD work by diverting the surge current to ground, protecting the connected equipment. SPD are available in a variety of types, including whole house SPD and point of use SPD. Whole house SPD are installed at the service entrance and protect the entire electrical system. Point of use SPD are installed at individual outlets or appliances and protect specific equipment. Proper installation and maintenance of electrical systems is essential for safety and reliability. Only qualified electricians should perform electrical work. Electrical work should always be performed in accordance with applicable codes and standards. Electrical systems should be inspected and tested periodically to ensure that they are functioning properly. Any deficiencies identified during inspections or testing should be corrected promptly. Electrical safety is everyone's responsibility. By following these guidelines, one can help to prevent electrical accidents and injuries. Understanding the principles of electrical grounding, bonding, and overcurrent protection is crucial for ensuring the safety of electrical systems. Proper installation and maintenance of these systems are essential for preventing electrical shocks, fires, and equipment damage. Always consult with a qualified electrician for any electrical work and follow all applicable codes and standards. The importance of electrical safety cannot be overstated. Electricity is a powerful force that can be dangerous if not handled properly. By following safe electrical practices, one can protect oneself and others from electrical hazards. Always be aware of the potential risks associated with electricity and take the necessary precautions to prevent accidents. Remember to always turn off the power before working on electrical equipment. Use insulated tools and wear appropriate personal protective equipment. Never overload electrical circuits. Do not use damaged or frayed electrical cords. Keep electrical equipment away from water. Teach children about electrical safety. By following these simple guidelines, one can help to create a safe electrical environment for everyone. Electrical codes and standards are constantly evolving to reflect new technologies and safety concerns. It is important to stay up to date on the latest requirements to ensure that electrical systems are installed and maintained in accordance with best practices. The National Electrical Code is updated every 3 years, and it is the most widely adopted electrical code in the United States. Many states and local jurisdictions also have their own electrical codes, which may be based on the NEC or may have additional requirements. It is important to be familiar with the applicable electrical codes in your area. There are many resources available to help people learn about electrical safety and codes. The Electrical Safety Foundation International, or SV, is a non-profit organization dedicated to promoting electrical safety. SV provides a variety of educational materials and resources for consumers, electricians, and other stakeholders. The National Fire Protection Association, or NFPA, is a non-profit organization that develops and publishes codes and standards related to fire, electrical, and other hazards. NFPA offers training courses and certifications for electricians and other professionals. Many community colleges and vocational schools offer courses in electrical technology and safety. These courses can provide people with the knowledge and skills needed to work safely with electricity. By taking the time to learn about electrical safety and codes, one can protect themselves and others from electrical hazards. Remember, electricity is a powerful force that should be treated with respect.